Good afternoon, everybody. Thank you for attending AWE in these circumstances where we can all gather once again. It's marvelous. I'd like to tell you a little bit about our company, Metamaterials, and in particular, the work that we're doing in advancing augmented reality glasses in particular by integrating functionality. We actually, as a company, have broad experience gathered over the last 15 years in metamaterial design, in holographic and diffractive optics, in biosensors, optoelectronics, and a variety of other disparate technologies. And what we're trying to do is to bring that together now around a cast ophthalmic lens platform, where within the lens itself, totally integrated, we can bring unique functionality that we think is going to advance AR glasses further than they've hitherto been done before. And in this talk, what I'm aiming to do is describe really how that works and how these smart technologies come together, to really permit that. And these technologies can include 5G and 6G antennas built in that are totally transparent, eyeglass displays that have eye tracking and other electrochromic type films such that you can dim from the outside world and hence not have to generate so much ambient lighting in your projectors, reducing bulk, reducing power, etc., etc. So these features are really critical if we're ever going to get to that all-encompassing pair of Warby Parkers that we're looking forward to. And our tenet is that it's fundamental material science and material systems that will enable us to do that. So we design and develop these and fabricate these metamaterials. We're probably the first company in the world under the banner of metamaterials. We went NASDAQ last year and bring with that the promise of these unique structures which are at nanoscale. So you're engineering materials here operating at nanoscale to do things that cannot ordinarily be done with conventional materials. And the other distinguishing feature is that we're already at a roll-to-roll process with these materials. So it really offers the opportunity to have a tremendous price point where we can actually deliver this technology to the masses, for an appreciable price point. So ARfusion, as we call it, really is the combination of this metamaterial science plus the ophthalmic lens. And as I mentioned earlier, we can combine these metamaterials to, for instance, reduce eye glow, so you don't look like an autonomer when you wear your AR eyeglasses. And dimming layers, I mentioned earlier. Holographic reflectors is one that we're a little bit famous for in the aviation community, having developed glasses along with Airbus so that all their pilots, as they land, can actually avoid laser flashing, which is very dangerous, as you know. So if you look at these AR smart glass requirements, they're really quite stringent. The glasses have to be, as I mentioned earlier, extremely comfortable, large eye box, always on, 24/7 use, or at least in terms of workers, at least a full working day, all day usable. They have to be rugged. If you've dropped them, they're not going to break. And critically, as I mentioned earlier, you have to embody technologies that can truly be delivered in volume and at a reasonable price. And that doesn't include some of the more esoteric technologies that are currently done at wafer level. So everything Meta do is fundamentally at the film level, offering this scalability and opportunity for that. So providing a prescription optics capability in the actual lens is fundamentally, right from the get-go, a difficult task. You have a classical optics industry providing optical solutions, ophthalmic optical solutions, that is extremely well entrenched, extremely efficient in delivering your glasses. How on earth can you compete with that? Well, it turns out that our acrylic UV curable lenses do compete. In fact, they compete very well, and I'll come on to show you the machine set and the tool set, which is largely roboticized, that can accomplish that. So we can actually manufacture very high quality acrylic lenses to any prescription and provide every prescription. And that, it turns out, gives us a very unique advantage. Because if we're to tailor a display to somebody's particular prescription at the same time as doing that prescription, we can align the films and create a display that is fully customized for that particular client in that regard. And I'll come on to show you how we add these other functionalities. So the lens casting system that we've developed is actually in several stages. We have over 2,000 sets of molds covering all the range of different prescriptions. These are loaded by a robot into the system, where we then inject monomer to actually UV cure it and create the lens itself, the plastic lens itself. After that, we go through a couple of steps, but largely it doesn't need too much refinement, doesn't need too much resurfacing or any other treatment, so we have a natural advantage in creating a lens that's already at ophthalmic quality almost from the start. And you can see some of the machines in action here. It's a very neat little line that we have, has a capacity which I'll go into in a moment, showing you. So the mold is selected from the library that's held in the repertoire. The monomer is then injected through 2 halves of these casts that are casting the lens for the particular prescription. And once the monomer is filled up in between those 2 casts, it goes in for curing. One of the unique things about these lenses also is that they suffer from very little birefringence. And you can see here then we separate out the 2 molds, revealing the lens, and go on to do a final heat cure on that. So this line is very automated, and you can therefore dial in the individual prescriptions and deliver the lenses at the output. It also has a fundamentally high throughput, which against some alternative methods of casting lenses used for augmented reality, we have a natural advantage. We have a high throughput from this casting system that isn't exhibited by other methodologies of printing lenses or doing them in a different way. And because of the very controlled UV polymerization that we have in the cast system, we get a very high quality product at the end of it, which is nice. And of course, you can see some of the advantage here where we can incorporate, which I'll come on to show in more detail, dimming films, sensor films, holographic films. All of these requirements are needed in AR as we go forward for eye tracking and various other control parameters. Many of these we've accomplished with our company, with our customers so far. So lens casting has production efficiency. It has very little offcuts and residual throwaway materials. It enables new products by being able to cast the materials into the lens, which I'll go through in a moment. And it allows you then to have active functionality within the lens itself. You can see here this keynote figure, 80 lenses per hour with one machine. Obviously, you can get more machines to accomplish this. It allows us to come out with lenses that are highly functionalized for AR with the display that are very cost competitive and totally transparent. And that's the other keynote feature of everything we do here, which is essential if we're to make effective AR glasses. So you can see here, just in the middle position there, which I didn't show in the video, where we insert the films and they're literally cast in situ and electrically connected, as I'll come on to explain in a moment. And afterwards, the molds are released and they're slightly cleaned and then reusable. So everything is reusable in that respect. So we can incorporate waveguides. We have a very active program in a unique type of holographic combiner. We have filters and electrochromic films. We announced this week, in fact, only on Monday, a partnership with PPG on advanced electrochromic films, essential so that as you move outside of the warehouse into the daylight, naturally the display dims, preventing the need to have an abundance of nits so that you can over-generate to compensate for the sunlight in that respect. And you can see here in this example of embedded holographic combiners, this is an area of excellence for our company. And with regard to that, I won't go into too much detail here because it's a whole area in itself. But my colleague, Andrew Mark, who's our Director of Photonics, will be having a talk on Friday, especially with regard to what we've been able to accomplish with these advanced displays. We're in partnership here with Covestro. And what's unique, and for the first time I can announce it publicly, is that we're now using Covestro material, holographic material. For those that are involved in holographic displays and areas, this is a big deal where we've been able to move away from the films that they've traditionally used to having liquid material, much higher quality, much higher specification in that respect. So incorporating holographic combiners, whether it's surface relief, whether it's other types of volume holography combiners, perfectly fine. We can incorporate air gaps, mesofilms, and various other structures to enable that in our glasses. One of the things you'll see right here is that we've been able to cast extraordinarily flat substrates. This will be competitive against Schott and Corning with regard to the base substrate used in waveguides. So we literally cast a flat with very, very high surface flatness and is suitable for incorporating then as a waveguide into the lens itself in that respect. NanoWeb is a kind of companion technology that we have at Meta, which is now a metal mesh technology. This is a nanostructured conformal metal mesh, and it directly competes and to a certain extent in these applications is far superior to indium tin oxide as a conductive material. Why is that important for AR? Because it gives us a fundamental substrate now to make what we incorporate into the lens an active device, an active focusing lens, an active electrochromic initiator so that we can turn the display that the user sees completely dark. And fundamentally, it is extraordinarily transparent and also exhibits properties such as only 1 ohms per square, which is almost impossible with an ITO metal film. The other big attribute is because imagine like a mesh can be conformal. We can wrap it over the lens. So this form of electrification, so to speak, within the lens itself is not only totally transparent to the user, but critically can be conformed around the actual surface of the lens during the time of fabrication. So this allows us also to pre-pattern circuits within the lens at the time that we create the mesh. So it's kind of lithography for free, so to speak. Although I call it lithography, and you might have in your mind an expensive process, wafer-driven, etc., this is today a roll-to-roll process. And in our facility in Pleasanton here locally, we have a full-blown roll-to-roll line delivering high-quality film. So this roll-to-roll lithographic manufacturing allows us to collapse the cost of this functionality again, enabling us to deliver it in that regard for a number of applications. One of them on our booth downstairs tomorrow is a lens that can self-clear. How many people have misting up when they're wearing a mask? We're all used to that. This is an everyday task for a lot of people that wear safety glasses in chemistry labs and various other places. This is not just a problem of this time, so to speak. So you can see on our stand that we can instantly clear a lens of any fogging, which is great for divers, great for any skier or snowboarder here that might like to have this facility, but critically with very high electrical conductivity, which means that we keep the power supply and the battery supply to the absolute minimum in that respect. You can see some of the other examples here where we have an array of cameras, so we can look at your eye for eye tracking. And embedded within that is the circuit itself to route all the data back. So the circuit is printed at the same time that the NanoWeb is created, which is a very unique capability that we have at the same time of processing. Electrochromic dimming, I mentioned earlier, we announced a partnership with PPG, who have excellence in this area. Have you ever heard of transitions in lenses? That's PPG. And so we're working at the front line with them to rapidly bring this capability for dimming to the AR marketplace in glasses for a whole variety of different customers across the board. And then finally, we're exhibiting for the very first time here at AWE 2022 a 5G antenna that's totally built into the lens. So why would you want an antenna totally built into the lens? Surely you can have a little antenna like you have in your cell phone along the leg of the lens. Well, it turns out that's a large surface area, and it has extraordinary gain characteristics for that antenna. And if you can't see it because it is totally transparent, you can have large antennas in each eye. 5G, 6G, up to the highest bandwidths capable. And why is that important? Because then we can start considering potentially other architectures which has a direct high bandwidth link with respect to transmitters in the room, or transmitters in the factory, or transmitters at different locations in say, your home, with that in mind. Because now we don't need to have the computer in the glasses. The glasses is acting as a very high bandwidth interactive receiver of signals that are transmitted from the side of the room, or from your computer, or from your cell phone, obviously, in terms of carrying that ordinarily. So this antenna and the capability of having that in such a large area really transforms this opportunity and this capability. We think will actually get people to start thinking differently about how we can make these glasses extremely compact, very powerful, and obviously linking to various applications, either cloud computing for AR or various other applications in that respect. So for high-speed data rates and low lag, which we have to have for AR, for image generation, this type of capability, whether it's telepresence for intuitive communication with somebody back at base, or whether it's for full stereoscopic AR applications with overlays, either way, this is the type of capability that can enable that, we think. So in summary, ARfusion from Metamaterials is a completely unique proposition, and really, I think, takes a whole step forward in terms of AR glasses, from where we've been with separate ophthalmic lenses to now embedding that ophthalmic lens with these properties that we all know that we need for next generation AR in that respect. And just a little point here in terms of comparison with other conductive films, we think that we're extremely distinguished in terms of very high transparency and very low sheet resistance, which is the name of the game when you're concerned about battery power. Well, thank you very much, and please come to our booth to see examples of this technology exhibited in interactive demonstrations and a full array of different components. And if you're in the hard work of creating new types of AR displays, please at least come and see us and express any interest you may have. Thank you very much. If anybody has any questions, I'd be more than happy to address them whilst we're here.
Mike Labrash has talked about electromechanically changing the focal length of VR experiences. Is there a nano solution to this instead?
You mean these technologies applied to VR? I couldn't hear you very well. Sorry about that.
Yeah, sorry. Mike Labrash has talked about building prototypes that electromechanically change the focal length.
Okay.
And is there a way around the electromechanical?
Yes, I think Michael's probably referring to vergence accommodation, where in this particular case, if you have the capability to very accurately and at nano level pattern certain lenticular patterns or various other structures such that you can create, high index liquid crystal lenses. That's exactly the sort of application this would be applicable to, where we can then create conical forms to give different refractive index. In other words, to automatically set the particular lens prescription you require. And the key thing is, this is being done at levels where we're only a few micron. And so the opportunity then is to have multiple layers which concatenate so that you can actually then create the whole range of different accommodation that's needed for that particular application. Now, today's solution requires that you have separate elements and that they're all lined up, and I think Michael's been working on that for a little while and exhibiting that openly at the other Meta. But I think that this sort of technology, because we're operating the nanoscale, is the sort of technology that will help move that along in that respect.
Cool. Thank you.
You're most welcome.
Hello, my name is Elizabeth, and I am a PhD student doing augmented reality for education. And I was curious, you were talking about how currently they have all of the different lenses. They're only separate. I think you just answered that in the last question. So I'm curious in terms of when you start putting all those together, does that increase the size of the lens? If you need high index or you have a very high, bad vision and you need really large, what happens with those aspects? And in terms of cost, because most time people get their lenses partially through insurance. So is that something that would be somewhat comparable, where you could say maybe 300, 400, which some lenses are, depending on your type of vision, that you can go and choose that option? Or is that something that would not be feasible for the average consumer?
Well, there's a lot of things there you're unpacking. Let's unpack that a little bit. The first thing to say is prescription glasses, to ophthalmic quality, will still require a doctor's certificate, with regard to the prescription. The refractive index that we're dealing with on our cast lenses is a little bit variable, but it doesn't go super high just yet. Now, there's ways of nanodoping that and dramatically increasing the index, but we're not there yet. So to the extent that we need a lot of optical power in the lenses, it will necessitate a more bulky lens, just the same way as lenses are today. But nonetheless, in terms of AR applications, at least you have a pair of glasses you can wear ordinarily that are so transparent, and you only switch it on as and when you need it for AR. So it's still, passing that litmus test, but we haven't solved the rocket science of very high index, other than the kind of previous question from the gentleman, where we can actually change liquid crystal, high index liquid crystal layers in a lamina that might then offer some additional correction in consort with the high index. So I think that, I guess another issue is insurance. Would insurance companies, well, why wouldn't they? Why wouldn't an insurance company, if you bought a pair of AR glasses that were ordinarily your prescription lenses, why wouldn't that be supported, providing it performed its ordinary task, and then you switch it on with your phone and activate it, and obviously you have the opportunity to have AR glasses, data glasses, whatever the application is. I don't see any reason why they wouldn't get behind it, providing it's a viable alternative and it's not too much of a cost delta.
Mm-hmm. I was curious if you could talk a little bit about the cost delta.
Which one, sir?
The cost delta.
The cost of them? I don't think that the cost will be any different than conventional glasses. If you look at the cost that it takes us to produce the output from the largely automated machine tool, it's very competitive. I mean, why doesn't that act as a standalone alternative to conventional glasses? Well, there's one or two barons of the ophthalmic industry there that pretty much have a closed shop. So I don't think that we necessarily would want to go face off to the conventional ophthalmic industry, and that's why really we're focusing kind of on next generation glasses which have the benefit of augmented reality enhancement.
Thank you.
You're most welcome. Great. I think I'm out of time, actually. Unless there's any other questions. Thank you so much again. All right. Okay.